All right, guys. So here's going to be your lesson for this Friday. Whether you're doing it now or doing it later, we'll see. But so when you come to dealing with limits of trig functions, when you're dealing with limits of trig functions, you're still going to go about the same process that you did before. That is, when you're dealing with a certain limit, as it approaches a certain value, you're going to take that value and you're going to plug it in. And you're going to do that, hopefully, to get an answer, because if you get an answer like 4 or 0 or -7, that's great. You've got your answer. Problem is, what happens when you get a number like 0 over 0 or a number over 0? That's when you've got to do some work. Now, actually, it's a little bit easier when you get an answer like a number over 0, because when you get an answer like a number over 0, we've already talked about that, right? When you get a number over 0, whether it's 1 or something else, you know that there's going to be a vertical asymptote there. And when there's a vertical asymptote there, typically, not typically, but when there's a vertical asymptote, we know that the limit does not exist. And sometimes we're going to write D and E. Most of the time we're going to write D and E. And occasionally you get one of those volcano situations. We'll talk about those as we move through there. But most of the time when I get a number over 0, I can say a D and E. Now, when I get a 0 over 0, which I'm talking about in the second situation on the trig notes in your in the book. When you get a 0 over 0, that means there's a hole. Now, if you remember our plan for finding a hole, our plan was to factor. Well, you're going to see it's hard to factor a trig function when it doesn't factor. So what we're going to do is we're going to take for granted a couple of rules that AP Calculus gives us that were proven by, well, not AP Calculus, but Calculus gives us, that are proven by something called the squeeze theorem. Now, we're not going to actually prove the squeeze theorem, mainly because it's not a calculus class. And even in regular AP, AB, you don't have to prove the squeeze theorem. I'm not sure about BC. So what we're going to do is we're going to learn a couple of little rules to help us find the limits when you do get 0 over 0. So again, hopefully we plug in the number, we get an answer, everything's awesome. Or we plug in a number and we get a number over 0, which means there's a vertical asymptote. The limit does not exist, except with special cases we'll talk about later. But occasionally we get a 0 over 0, which means there's a hole, and holes have limits, and we've got to find them. And here is the process that we're going to go by. I'm going to walk you through a few of them. Now, what I'm showing you first is going to be a little trickier than what I'm going to show you next. And this is what most colleges require you to do. The first thing they require you to do is to actually show that these rules exist. Few of them are pretty obvious. If I plug, and I'll show you those, I don't need the squeeze theorem for. I would actually need the squeeze theorem, which again, I'm not going to get into, to prove these last two. But we're going to assume that somebody did that proof, like we do in a lot of cases in math. And since it's been proven, that theorem, we're going to use these two situations to be able to do all these trig limits. I'm going to show you again a few of them. You're going to go, oh, this is a lot of work. And then I'm going to show you my way of doing things. You got to learn a couple of other options, but it makes your whole world much more simple. So let's get started. First few things we've got to know are these 5 rules, okay? And let me boil them down for you. They essentially say a limit of a sine function as x approaches 0. Now, if I plug a 0 in there for x, it doesn't matter what the a is. 0 times a is 0, and we know from the unit circle that the sine of 0 is 0. So anytime I'm plugging a 0 in there, the sine of a 0 is going to give me 0. Okay, now you might go, well, what if it's not 0? Well, if it's something like 5, I get the sine of 5 times a, and I type in sine of 5 times whatever that a is into my calculator or whatever, and I find an actual value, or I use my unit circle if possible. So again, we're talking about situations that give us trouble. So this is a lot of the situations that give us trouble or concern occur at 0. So we're talking about that a little bit more now. Okay, second thing is, if I have a limit of a cosine function, well, if I plug a 0 in there, again, 0 times any a value in there is 0. But this time, the cosine of the remaining 0 is equal to 1. You know that from the unit circle, because at 0 radians, or 0 degrees even, the x value is 1. Okay? Now, tangent, we know that tangent is defined as sine over cosine. So if I plug a 0 in there, I go to 0 degrees, because it's tangent of 0, right? The a goes away again. And at 0 degrees, the y value, which is 0, over the x value, which is 1, is also 0. I'm not going to keep thinking about the unit circle all the time, although I can. I'm just having those three memorized. Now this, there's a couple ways to prove that. One is the squeeze theorem. The other is to graph it. If I graph the function sine of x over x, or if assuming u is an x value, if I were to graph that, you'll see this function kind of oscillating like this. And when it gets towards 0, it goes and it jumps right up there to 1. All right. And there's a hole there. You can't really see that on your calculator when you graph it. But if you enter the value x equals 0, you'll see that it's undefined. So there's actually a hole there. Okay. But the limit is, the graph is approaching that hole that is at a height of 1. But let me ask you a question. Before you wrote that number 1, if you were doing this limit, you probably would have plugged a 0 in. And if you plug a 0 there and there, the sine of 0 gives you 0 over 0, and that means there's a hole, right? Now, that's not my answer. Holes, we normally go and factor and cancel. I can't factor a sine, okay? So we have to know this property right here to be able to continue. And this property was proven by something called the squeeze theorem. So let's just chalk this up to a rule and then go with it, okay? Now, if the sine is on the bottom or the sine is on the top or the bottom, doesn't really matter. Think about it. If I plug a 0 in, I still get 0 there. If I plug a 0 there, I get sine of 0, which is there. And again, that gives me 0 over 0. Not an answer, means there's a hole. But if there's a hole, there is a limit. Okay, 99% of the time, if there was 100% of the time, there actually is a hole. But when it gives you 0 over 0, most of the time that means hole. A couple of weird exceptions, which we'll get to later. But again, this, because somebody proved the squeeze theorem, is equal to 1. And again, if you graph this thing right here, y equals that, but use x's, you see that the graph has a hole right there at 1. So these are the 5 things that I'm going to use. And the fact that every trig function can be written as sine and cosine means I can even take stuff like tangents and secants and cotangents and rewrite them as sines and cosines and use this information. So let me show you a couple, and I'll actually have them solved for you, and then we'll do a few on our own, and hopefully I'll convince you how sick you are of this, and then I'm going to show you a modified version of this, which is still pretty easy to do. And ultimately, when we're done with all this, we're going to learn something called a derivative. And when we learn derivatives, we'll be able to apply something called L'Hopital's rule. And L'Hopital's rule will give you another option for doing these trig functions when you get 0 over 0. Now, let me remind you, all of this I'm showing you is a way to help you for problems that give you zeros over zeros. If it doesn't give you 0 over 0, you're not going to do any of this junk. Okay, you're going to see that probably all of these, if they give you an answer, great. It's when you get the 0 over 0 that you're going to have to apply and use these strange techniques I'm going to show you. Okay, so let's get started. Look at number 1. Number 1, they give you this example. It says the limit of this weird trig function as x approaches 0. Now, you know from the little limit properties I gave you on day 1 that if you have a limit added to another limit, you really could do them separately. So I'm going to do the limit of this and the limit of this. But if you want to do them all at the same time, you can. But the first thing I'm going to do is plug that number in. It tells me to go to 0. So if I plug a 0 there and there, I get this. Well, from the rule that I just did, sine of 0 is 0. Cosine of 0 is 1. Drop the 2 and the 3 down. 2 times 0 goes away. 3 times 1 is 3. I am finished with this problem because I got an answer. Awesome. That is my hope. It is rarely going to happen on this test. Over here, I plug a 0 into this function. I'm hoping I get an answer. 0 squared plus 1, 1 minus sine of 0. Well, 0 squared plus 1 is 1. Sine of 0 is 0. 1 minus 0 is 1. 1 over 1 is 1. Great, I've got an answer. I'm very happy. Again, not going to happen very often. What's going to happen more than not is you're going to get 0 over 0 or a number over 0, and you got to know what to do. So let's check out number 3. Number 3, I should have written this, but I didn't. But again, I jumped right to this process. But what I really did was plug a 0 in. When I plug a 0 there, I get 0 times 3 is 0. When I plug a 0 there, I get 0. Sine of 0 is 0. and I'm right here. Now that means there's a hole, okay? But we know that at holes, there are limits. So I've got to figure this out. And the only thing that's going to help me is those rules right there. So let's see if I can make this work. All right? So since I got that, I know there's a hole, I'm going to try to apply these rules. So here's what I'm going to do. I'm going to take this sine of 3x and that x. Now, according to this rule, look up top. According to this rule right here, if whatever I'm signing is the same there as it is there, if that's true, then the limit of that is 1. But these would have to be the same. And in this problem, they're not the same. You see that? This one's 3x and this one is x. But what if I multiply the top and the bottom by 3? Now, this 3 is going to be sitting out there by itself, but I could take this 3 and multiply it by x and get 3x. This now and this now are the same value. This is like sine of u over u. And what is sine of u over u as I approach 0? Well, it is 1. And since this 3 is still sitting out there by itself, I carry it along, and I get 1 times 3 is 3. And the limit is 3. Great. Easy enough. Let's try number 4. Number 4, again, don't jump into these rules. We're hoping when I plug a 0 in that I actually get an answer. Let's try it. Plugging a 0 there. 4 times 0 is 0. Tangent of 0 is what? 0 from the rule above. Plug in a 0 there. 5 times 0 is 0. And here I am. Well, what does that mean? It means there's a hole. It's not an answer. It just means there's a hole. And since there's a hole, I've got to try to figure out where that y value of that hole is. Well, guess what? Tangent is not one of my rules. The only rules I have, well, tangent of 0 is. But that's not really helping me here. So here's what I'm going to do. I'm going to rewrite tangent of 4x as sine of 4x over cosine of 4x. And I'm just going to take this 5x that doesn't really go with anything and slide it out to the side. So here's me sliding the 5x out to the side and taking the tangent of 4x and writing it as sine of 4x over cosine of 4x. Okay? Now, I'm trying to kind of eliminate my hole. And the way to eliminate the hole is to be able to use this or this. These are what eliminate holes, because both of these answers gave me 0 over 0. But if I can write them like that, I can cancel that part out, and it's equal to 1. So here we go. I am going to, and again, I've told you this is not the fun way to do it. I am going to try to get this sine of 4x over a 4x, because sine of 4x over 4x is a u over a u. Let's see if I can do that. Okay, so I am going to leave the sine of 4x there, and I'm going to take this cosine of 4x, and I'm going to slide it over here with the 5. See that? And then I'm going to slide this x under there. Now, initially, that gives me sine of 4x there. The x gets slid over, and then I take the cosine of 4x, get it away from that, and put it over here with that 5. But I don't have the 4 that I need, so I multiply the top and the bottom by a 4. And when I do that, what does that give me right here? It gives me sine of 4x over 4x, which is equal to what? That's sine of u over u. And sine over u is 1. So I can replace all of that right there, right? All of that right there, I can replace it with a 1. Now, because I've dealt with that, all I have to do now is the limit of this part. Well, guess what? Cosines don't give me issues, right? When I take the limit of this part, I got a 1. But when I take the limit of this part, I don't need a rule. Plug in the 0, and what happens? 4 times 0 is 0, but what's cosine of 0? 1. 1 times 5 is 5, and I'm left with 4/5. So I have a 1 times a 4/5, which is my limit. Now, again, when you get 0 over 0, your goal is to split up these trig functions and try to get sine of u over u. And it may look like sine of 4x over 4x, sine of 3x over 3x, sine of 1x over 1x, sine of 8x over 8x. Those are the things you're trying to make happen. And when you do that, that's the way essentially that you cancel out the common factor of the whole. All right? Now, we always canceled out common factors when we had wholes before. We didn't need the squeeze theorem, but you could technically use the squeeze theorem for those. Here we need the squeeze theorem. We don't teach it. So what we're going to do is accept that principle that sine of u over u as u goes to 0 is always equal to 1. And if I can make that show up in my problem, the rest of it will have a value, and I can just multiply that. All right, so let's check out number 5. All right, don't give you any hints on number 5. So on number 5, you've got 2x and sine of 7x. Now, for this to work, I would need 7x over sine of 7x. So here's what I'm going to do. I'm going to take that 2. I'm just going to put it out there because it's times 2, right? Now, I want this to be 7x over sine of 7x. Well, I can make that happen by multiplying that by 7 and that by 7, top and the bottom. Then, when I take the limit, what is the limit of 7x over sine of 7x? It's 1. And what's the limit of a constant? Well, you just bring that constant down, and you end up with 2 7s. Okay? Now, this one, a little bit trickier because you have this x plus sine x over x. Well, whenever you have a plus in there, you might already be thinking this. I'm going to put this over this and this over this, and I'm going to create 2 different limits. So I'm going to have the limit of the x over x, which is just, well, I'm going to write x over x, but that's just 1. Plus, I'm going to have the limit of the sine x over x as x goes to 0. Now, this is not even a trig problem. When I try to evaluate this limit, I get 0 over 0. What's my rule when I get 0 over 0? If I can cancel a factor, I cancel it, and I'm left with the limit of 1. Well, the limit of a constant is itself, always. All right, then I get over here. Well, look, sine of u over u. Those two things match. So if I have sine of u over u as x goes to 0, that's always equal to 1. And again, if I had plugged 0 in, I would have gotten 0 over 0, right? But that because of this rule, it's located up top here in one of those 5, that's equal to 1. So I get 1 plus 1 is 2. All right, let's jump over here to number 7. Okay, I've got this tangent squared. Okay, if I plug a 0 in, I get tangent of 0 squared over 2 times 0. Tangent of 0 is 0. 0 squared is 0 over 0. What does that mean? It's not my answer. It means there's a hole. Well, how do I get rid of holes? I got to try to turn this into a sine of u over u. So let's try it. What's tangent squared of x the same as? Tan x, and then I've got this 2x here. If you want, you can just put that 2x on the bottom over here if you want. Okay, and you can take this step if you want, or you can skip this step and say tangent x is really what? So this is kind of what I have right here. Tangent x is sine x over cosine x, sine x over cosine x. You tracking with me? Okay, now my goal is to get rid of this hole, or whatever it is, by turning this into a sine x over x, or sine u over u. That means these cosines don't need to be down here. So I'm going to slide these cosines over here, both of them, and just put cosine squared there. Now they're out of the way. Now, here, I really want to have an x there and an x there. So I can put an x on the bottom as long as I put an x on the top. And I could put an x on the bottom here and put an x on the top here, right? And then now when I look at this, I go, all right, the limit of sine x over x is 1. The limit of sine x over x is 1. Here, one of those x's cancels. And when I plug a 0 here, I get 0 on the top. 2 times what? What's cosine of 0? 1. 1 squared is 1. 1 times 2 is 2. And I'm multiplying the number 1 times 0. That's fine. And I get 0. These are pains, aren't they? right? I'm going to do one more or maybe two more, and then I'm going to show you some of my tricks, and the tricks are going to make it a whole lot easier on you, okay? And if you go to Cal 1 in college, hopefully you'll pass the AP test, and you won't have to take Cal 1, but some Cal 1 teachers make you use the squeeze theorem and do all of this. Totally waste of time in my opinion, but whatever. When in Rome, do as the Romans. All right, last one. All right, oh, sorry, number 8. Right here, I've got tan squared x over 2x squared. Limit as x goes to 0. If I plug a 0 in there, I get tangent of 0, which is 0. 0 squared is 0. I get 0 squared, which is 0. 0 times 2 is 0. What does that mean? It's not the answer. It means there's a hole. There are limits at holes, so I got to find it, which means I got to try to eliminate the hole by rewriting this as sine of u over u, or sine of something over something where the somethings match. See if we can do it. Okay, well, this is a tangent x, and this is a 2x squared. So here's what I'm going to do. I'm going to change the first tangent, which is on the top, to sine x over cosine x. The next tangent, which is on the top, to sine x over cosine x. And then the 2x squared, which is not on the top, I'm going to put it out here to the side. Okay? Now, clearly, I don't want sine over cosine. I want sine of u over u, or sine of x over x. So I'm going to take both those cosines, and I'm going to slide them over to here. So I'm going to take that one and that one, bring them over here. And you know what? I can put an x there as long as I put an x there, and an x there as long as I put an x there. And that's totally fine. I'm going to show you that right here. X, 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 another x. Look, they cancel. So I'm left with just 1 over 2 that, right? But what I also could have done, let me go back and show you what I had. But I also could have done, okay, is just take that x squared and move it over here and get rid of it that way. That works. I could have done that over here too. I could have taken one of those x's and put it right there, and then just replace the other ones that I need on the top and the bottom. So either way, if you like putting x, 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 and then canceling, that's fine as well. Well, anyway, now, what does the limit of sine x over x give me? 1. What does the limit of sine x over x give me? 1. And then, because that's a rule. Now, there's no rule here, but so let's plug in a 0. What's cosine of 0? 1. What's 1 squared? 1. What's 1 times 2? 2 on the bottom. And what's 1 times 1 times a half? 1/2. You with me? Okay, let's check this. Last one, I'm going to erase this right here. Erase this. So last one, I plug a 0 in there. 5 times 0 is 0. Tangent of 0 is 0. 2 times 0 is 0. Tangent of 0 is 0. Okay, not an answer, but it tells me there's a hole. What do? I've got to rewrite it as sine of u over u. Okay, I got a little work here. So I got a tangent on the top. So this tangent of 5x is the same thing as sine of 5x over cosine of 5x. And then I've got this tangent on the bottom, which is the same thing as sine of 2x over cosine of 2x. And if I take a fraction to divide by another fraction, doesn't that mean I multiply by the reciprocal? So I really have the cosine of 2x on the top and the sine of 2x on the bottom to replace that bottom part. Now again, got to get rid of what's giving me the hole. So let's find the sine of u over u. Well, clearly, sine of that doesn't need to have a cosine in there. So I'm going to slide that cosine of 5x out. I'm going to slide that cosine of 2x out. And what do I need there and there? Well, I need a 5x there, so I'm going to multiply 5x there, but I've got to have a 5x, I've got to have a 5x on the top too, so I can put a 5x on the top. And then I need to have a 2x there, which means I'm going to have a 2x on the bottom, so I'm going to put a 2x on the bottom there. And while I'm at it, I can cancel those out because I don't need those. What does the limit of that give me? 1. What does the limit of that give me? 1. Again, why? Because of those first 5 rules that I had and were memorizing. Sine of u over u or u over sine u. And then those They don't have signs in them. No worries. Plug in. Let's see what we get. Plug in a 0 there. 2 times 0 is 0. Cosine of 0 is 1. 5 times 0 is 0. Cosine of 0 is 1. And then since the x's canceled, all I have left is 5 halves. When I multiply it all out, 5 halves. All right? Now, you may like this. If you like it, great. But I can tell you, I can look at this problem and tell it's 5 halves just by eyeballing it. I can look at this problem right here and tell you it's 2/7 just by eyeballing it. Okay? I can look at this problem right here and tell you it's 4/5 just by eyeballing it. So I'm going to show you some tricks so that you can eyeball a lot of these. Now, some of them you still got to do a little work, but let me just show you. So here are the tricks. And again, for an AP Cal class, you're just looking to evaluate these limits. And the quicker you can get them, the better, and move on. You don't have to show all these steps and processes, but that's the real thinking. And again, we were taking these two rules for granted, which if you graph them, you can see that they're true, but we take those for granted, but they would have been proven by the squeeze theorem. These are just obvious, plugging it in and getting values. Now you'll notice I have never dealt with secant, cotangent, cosecant. If I'm ever given a problem with a secant or a cotangent or a cosecant in it, secant, cosecant, cotangent, any of those, including tangent or whatever, I guess, if I'm given those, actually, let me go back. If you're given a secant, a cosecant, or a cotangent, flip them, take the reciprocal, and write them in terms of sine, cosine, tangent. And that way, it's going to fit our narrative a lot more. So here's, even before I reminded people or talked about where the real math was coming from, here's the way I figured out in college how to do these limits very quickly and easily. So here's what I'm going to show you. All right, flipping the page. Here are the situations, and I know it looks like a lot right now, but I'm going to simplify it into a couple thoughts, okay? Now, you'll look at all kinds of ways I could put sine of something x over something x over sine of something x, okay? Sine of something x over sine of something x, sine of something x over tangent of something x, cosine of something x over sine of something x. I have tried to put every possible scenario of putting sine of x over something x, vice versa, cosine of something x over something x, vice versa, tangent x. I put every possible combination I could think of up here. And the ones that I've boxed, you can see these. The ones that I've boxed, all of those are situations that give me 0 over 0. You will notice none of those situations have cosines in them, because cosines in them give me 1s. And sometimes 1 over 1 is great. It's equal to 1. Sometimes you get a 0 over 1. That's great. That equals 0. Sometimes you get a 1 over 0, and because it's not squared. DNE, because there's a vertical asymptote. Right? And then sometimes even with sine, doesn't exist. 0 over 1 is 0. But the situations that are boxed are the situations that give you 0s over 0s. Now you'll notice I intentionally used different letters for A and B. That means that that means that they could be different, it could be the same, but they don't have to be the same like they were in the problems I was just showing you. You don't have to make them sine of 4x over 4x, sine of 2x over 2x. It could totally be sine of 2x over 3x. But the pattern that I've noticed is that when all is said and done, if it is one of these 8 situations, ignore this one for now. If it's one of those 8, then all you have to do is take the A value, put it over the B value, and you're done. A over B, 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 A over B. You're done. You don't have to do all of this garbage that I was just showing you. Now, it's not garbage because there's math behind it, but you don't have to waste time doing it. Now, things that I want to point out. I don't want you to memorize all 8 situations and be able to write them down. I want you to remember that basically all 8 of these situations boil down to these 2 things, maybe 3, okay? You will see that all of these are either a trig function of something x over something x, or it's a something x over a trig function of something x, or it's a trig function of something x over another, whether it's the same or different, trig function of something x. Look, this one and this one are trig functions of something x over something x. This one and this one are something x over trig function of something x. And then these other four are trig functions of something x over another trig function of something x. They're all equal to a over b. Now you'll notice that none of these situations have squares in them. So if you have a squared in them, like we did before, you need to break them up and do two different limits, right? So if there's, and all of these have x's on the bottom. If there's not an x on the bottom, doesn't fit one of these three conditions. But if it does, and when you do the limit, you get 0 over 0, right? And you got to check that, because sometimes you don't get 0 over 0. When you don't get 0 over 0, you're going to get different outcomes. So if you get one of these situations, and when you do the limit, you get 0 over 0, if that's the case, a over b, a over b, a over b, every time. And you don't have to go through all this mess. So let's take a look, see how this works out for us. And I think that you'll see it's a lot easier to get these things done quickly. Oh, by the way, this last one, you're going to have to memorize that for now, okay? You can graph it. If you graph y equals this, and then you go to x equals 0, you'll see that there's a hole there. Sure enough, if I plug a 0, then I get 1 minus 1, which is 0 over 0. There's a hole, but the limit is at 0. There's a hole at 0. Now, there's really no way to show you this other than graph it or use L'Hopital's rule. But I will test that on this test. It'll probably be worth a point or two. I'm telling you now. By the way, I could even switch the order there because it still gives me 0 over 0. All that does is negate it. I mean, negating a 0 is still 0. But you are going to have to know that one. But that's the one that doesn't really fall in line with all these other ones. It's just a random one I wanted you to know. Okay, so let's check it out. Check out number 10. Now, do you have a trig function of something x over something x? Whoa, tap the brakes. You got a squared. So because I have a squared, I'm going to rewrite this as tangent x over 2x times another tangent x. But it's not over 2x. There's two tangents, but just one of those. So I'm just going to put that over a 1. And I'm going to take the limit. Oh, by the way, before I start, I would have already plugged 0 in. When I plug 0 in that, I get 0 squared, which is 0, over 2 times 0, which is 0, which means there's a hole. So my rule has been checked. When I have a hole, I'm going to see if I can rewrite this and use my newfound tricks. So now that I've rewritten it into tangent x, 2x, and 1, check it out. That is a trig function of something x over something x. And it gives me 0 over 0. So what do? I take the a, which is 1, the b, which is 2, and I get 1/2. Then I go over here and take the limit of this one. Well, if I plug a 0 in there, I get tangent of 0, which is 0, divided by 1, which is 0. And what's a 1/2 times a 0? Not a 1/2. It is a 0. And I'm done. Let's try this one. Oh, cosecant. I don't deal with cosecant. So if you have a cosecant, you take the reciprocal, which is 1 over sine of 4x. So that changes to a sine of 4x in the denominator. All right, so if it's in the numerator, now it's in the denominator as a sine of 4x. Oh my gosh, if I plug a 0 in there, I get 0 over 0. Do the math. What does that mean? Do I have a something x over a trig of something x and got a 0 over 0? I do. A over b, 3/4. I'm done. Not that, 3/4. Check out this one. Now that's a constant, right? Constants I can ignore for now, right? So that I'm going to end up with 5 times something. Let's plug a 0 in there. 7 times 0 is 0. Sine of 0 is 0. 0 times 5 is 0. 2 times 0 is 0. Okay. Do I have so I know there's a hole. It's not my answer. I know there's a hole. Do I have a trig function of something x over something x? Yes. And did I get 0 over 0 from it? Yes. So what do? 7/2. Now, the 5 out front, drop it down, and what do I end up with? 35/2. Let's come over here. Plug a 0 in. 5 times 0 is 0. Sine of 0 is 0. 0 squared is 0. 0 times 3 is 0. 2 times 0 is 0. There's a hole. Not an answer, just means there's a hole. So what do I do with this? Well, it looks like a trig function of something x over something x, but the squared's bothering me. So here's what I'm going to do. I'm going to write that sine of 5x twice. Okay? And now I have the sine of 5x over 2x times a 3 times a sine x over 5x. Now, when I plug a 0 into 3, which I can't, do I get 0 over 0? No. Limit's 3. When I plug a 0 in there, do I get 0 over 0? Yes. Is it a trig something of something x over something x? Yes. 5/2. When I plug a 0 in there, I get 5 times 0 is 0. Sine of 0 is 0. That's an answer. 0. Multiply them all together, your limit is 0. You track it with me. All right, here, plug it in and I get 0 over 0. So I know there's a hole. That means that I know there's a limit. But there's squareds here. Well, let's think. It's not the 2x that's squared. It's just the x that's squared. And it's just the tangent that's squared. So I'm going to rewrite this as tangent x, and I'm going to leave the 2. Yeah, you can move the 2 out to the front if you want. Make it a 1/2. Take the x, split it up. You could leave the 2x with that. Doesn't really matter. Now, when I redo this limit, I do the limit of each part. It's really annoying. What's the limit of the 1/2? Well, just 1/2. What's the limit of tan x over x? Well, if I plug a 0 in there, do I get 0 over 0? Yes. Is that a trig function of something x over something x? Yes. Coefficient over coefficient, 1. Same thing here, 1. 1/2 times 1 times 1, 1/2. What about this? Plug a 0 in. 5 times 0 is 0. Sine of 0 is 0. 3 times 0 is 0. 2 times 0 is 0. Tangent of 0 is 0. I get 0 over 0. Not an answer. It means there's a hole, though. Ignore the 3. It's a constant. Do I have the trig function of something x over the trig function of something x? That was one of my 3 conditions, right? If I have that, then all I got to do is drop the 3 down. Coefficient a over b, 5/2. So multiply together. You starting to see this a little bit? I'm talking to an empty room and asking questions. It's been a long week. Okay? I'm going to leave that. Well, got it? All right. So, last little row. 16. I don't like cotangents. So this cotangent is really 1 over tangent, which moves that down to the bottom and makes it a tangent of 5x there. This cotangent of 2x is a 1 over a tangent of 2x. When I divide by a fraction, I multiply by the reciprocal, which puts that tangent of 2x up top. So basically, they just flip-flop. By the way, if there was a number out front, like this 4/5, that's different than the 3/7. The secant of 3x does become a cosine of 3x on the bottom. But that 4 is sitting there by itself. It's fine. Don't move that down with it. That's a times 4. 4 is fine. 5 is fine. It's the numbers that are on the inside that have to go with it. Okay, so be careful about that. These were on the inside, so they had to follow them up and down. Now, oh my gosh, I plug a 0 in there. I get 0 over 0. It's not an answer. It means there's a hole, though. Is this a trig function of something x over a trig function of something x? It is. A over b, 2/5. And that was a lot easier than changing everything to sines and cosines and trying to do sine u over u and all that stuff. Right here. This is arguably one of the more missed questions on the test. People start getting sloppy. They look up here and they go, oh, trig function of something x over trig function of something x must be 3/4. No, why not? You forgot to check to see if you got 0 over 0. What happens if you plug a 0 in there? 3 times 0 is 0. Cosine of 0 is 1. 4 times 0 is 0. Cosine of 0 is 1. I didn't get 0 over 0. I'm done. Okay? Look up here. I don't deal with secants. So secant of 3x becomes a cosine of 3x in the denominator. 4 stays there. Secant of 7x becomes a cosine of 7x in the numerator. 5 stays there. So this is really what I have. All right? So now that I'm to this, the biggest mistake I see is, oh, drop the 4/5 and then trig over trig, write the 7/3, multiply it out. Why not? You forgot to plug the 0 in. If I plug a 0 in there, what's 0 times 7? 0. What's cosine of 0? 1. What's 1 times 4? 4. What's 3 times 0? 0. What's cosine of 0? 1. What's 1 times 5? 5. You've got to remember to plug it in first and see. Well, get rid of the secants because we don't deal with secants, cosecants, and cotangents. Go ahead and flip those, get them in the right spot. But after that, plug it in, see what happens. Sometimes you get answers, right? Sometimes you get answers. Sometimes you get this, and when you do this, that's when you go to your rules. Okay? I'm just going to pick out 1 or 2 more just random ones. Look at, oh, I don't know. Look at number 6. This is on your trig limits practice. Number 6. Plug in a 0. 0 squared times 2 is 0. 0 minus 0 is 0. Sine of 0 is 0. Okay, not an answer, but there's a hole. I got to make this look like something. Well, there's a minus there. What if I put that over this and then that over this? So that gives me 2 separate problems. All right, so I've got the limit of the first part and minus the limit of the second part. Now, if I plug a 0 in here, I do get 0 over 0. But that x squared is bothering me. So what do? I break it up. So I'm going to take one of those x's. I'm going to leave that there. I'm going to take one of those x's, put it out here, just over a 1. And I'm going to treat this now like 3 separate limits. All right? So this part, look, plug in a 0 and I get 0 over 0. Is that something x over trig function of something x? Yes. And I would have had a 0 over 0? Yes. A over b. That part's done. Now what if I plug a 0 in here? Wait, does that give me 0 over 0? Yes. Is that something x over trig function of something x? Yes. A over b, 2 over 1. Now when I plug a 0 in that, I get 0 over 1. And when I drop down the negative 1, I end up getting what? 0 minus 1. So problems can be tricky. See what you can do. We've still got 2 or 3 days before the test. You got a whole weekend, a lot of worksheets to be working on. Sorry to do that to you, but I'm really trying to get all this stuff in before the AP season starts, which is going to be decimated. We're actually going to be floating around different classrooms. It's going to be a lot going on at that point. So do the best you can. Get the solutions out. Make sure you understand why or why not you're missing stuff. And we can answer any questions you have. Remember, this is the end of the new material. From this point on, we're just looking at different weird things, how they can occur, what's going to be going on, and hopefully we'll get you in a good shape for your test on the Wednesday we come back. All right? Take care. Have a good break.